So let's have a look at how to localize within maps, okay? As we saw, self-driving vehicles are basically an extremely safety critical modern day application of robotics. And leveraging maps does have performance and safety advantages in areas like perception, motion forecasting, and motion planning. But of course, in order to leverage any prior maps, like the stuff we saw in the previous section, the vehicle must know its position within them. And this is the task of localization. So in this talk, we will begin by specifying what localization is, how it's typically approached and why it's challenging. We'll talk about how to quantify how good a localizer is, as well as how to compute the ground truth. We will then discuss localization at more of a systems level in order to understand how accurate it actually needs to be. And this will yet again touch on these questions on how much we actually rely on the prior map versus how robust we are without it. And after this, we'll also talk about the methods for localizing and cover two major subtypes of localization. We'll do online localization first, which is essentially keeping track of your pose over time, starting from a known estimate. And then we will discuss global localization. So global localization basically means estimating your sensor pose without any prior information where you are located in the environment or with very, very weak prior assumptions. So given a sensor observation in a pre-built map, the task of localization is to infer the location of the robot within the map. And we focus explicitly in this talk on map-based localization, that is localization within a prior map, since this is what is basically necessary in order to leverage the maps we saw in the previous section. And formally, we wish to model the robot's belief over its state space, where for localization, this state space just corresponds to its position in the world. Although if you have robots with arms and other actuators, this becomes more complicated, but that's not the point here. So this is conditioned typically on some sort of observations, which are, GPS reading, LiDAR, whatever, and conditioned, of course, on the prior built map or M. So what kind of sensors can we actually use to localize? Well, the Global Navigation Satellite System, or GNSS, is a common source of input, which is very, very commonly used for initial pose estimates, at the very least for global localization. Estimates which you then refine with LiDARs or cameras. And of course, you can also use inertial measurement units or IMUs and wheel encoders as sort of complementary cues to these sensors, because they provide information that very well completes the degrees of freedom that might not be easy to observe otherwise. In terms of maps, there's a ton of maps and prior representations that you can use to localize against. And we go through a few examples, although there are tons of categories. So we saw in the previous section how these semantic HD maps can be built and annotated with information like lane boundaries, lane types, signs, etc. And these kinds of maps can also be used directly for localization. And even more lightweight topological data like raw OpenStreetMap data can also be used to localize within it, although this is a little bit less reliable. You can also use 3D geometric models to localize against, so they can be represented as dense or sparse point clouds, circles, or any other kinds of 3D primitives. And of course, the recent rise of implicit neural representations for rendering has also made them a prime candidate that people have been investigating for localization applications. So for example, it is possible to reference a novel camera image into an existing neural radiance field or NERF. And last but not least, you can also use simple occupancy maps, which are typically represented as some sort of top-down view of the world. And these maps can also contain additional attributes like the intensity or the color or the semantics of the things in the world. And they have the advantage that they can encode very rich information about the structure of the world, while also being a bit easier to store than things like 3D models and so on. And of course, there's many other representations that are not mentioned here, like databases of georeferenced observations and so on. The main characteristics we would like from a self-localization system that runs at scale are low costs, because we naturally want to map and localize in very large areas. You want the ability to localize in real time. You want to have high accuracy, preferably centimeter level accuracy, and you want to be robust. So you want to be able to handle and recover from failures. But in order to achieve these goals, there are still challenges like occlusion and geometrically degenerate areas that are challenging for localizers. In this particular case, geometrically degenerate means there are many possible solutions for aligning a new observation to an environment. So, maybe you have a very repetitive or very non-descriptive environment. Sensor noise is also another issue that affects, both cameras as well as LiDARs and GPS. And environmental changes like construction can also mean that localizers must be able to adapt to cases where maps themselves become outdated. So now that we know these properties that we want in our localization system, how do we actually know that we've achieved them? And this is the motivation behind discussing, metrics and ground truth, because without them, we can't really tell when we've achieved something that we aim to achieve. So it's important to, just like it's important to develop models and metrics for image classification and object detection, and it's impossible to do so without well understood metrics and benchmarks, the same applies for localization. So we wouldn't be here with the progress that we've seen in computer vision more broadly without large scale benchmarks and well thought out metrics. So all of autonomy happens downstream from localization. So any issues with localization can lead to problems in downstream modules like detection and motion forecasting and motion planning. So in order to ensure that localization acts as a solid foundation, we really, really need to figure out the right metrics to guide its development. We will cover several of these metrics in the coming slides. And later, we will also look at a possible methodology for actually quantifying the impact of localization errors on downstream tasks. So the simplest method to compute localization errors, which is also very rich as a building block, is absolute trajectory error, or ATE. The idea here is that given n poses estimated by your brand new localizer and n ground truth poses, in the case of ATE, you simply compute pairwise errors at every time and aggregate this information as a mean over the entire sequence. So, for example, in the illustration here, you have your ground truth trajectory in black, you have some brand new localizer with the blue trajectory, and then you can basically just draw a red line between the estimated and the ground truth position at every one of the n time steps. And this is the absolute error at that time. And then you can, of course, decompose these residuals before you average them. So you can only compute rotational errors or translational errors or whatever, which can actually be very beneficial. So, for example, if your car is driving in a city and you have these translational errors, you can maybe decompose your translational error into vehicle relative X, Y, and Z, and then focus your analysis on X and Y because they are more important for safety than Z alone, because we know that Z, which in this case we're assuming is up or height, will not change meaningfully with respect to the road. So if we're roughly correct about the Z, as long as we're not completely off, it matters less than, for example, the lateral error. Another brief thing that I wanted to bring up is the fact that ATE does assume that your candidate trajectory and your ground truth trajectory are in the same reference frame. And this is usually the case if you're localizing within a known map, because your ground truth will be with respect to the map and your localization poses will be with respect to the same map. But if you're doing a different or a slightly different kind of task, it might not be the same. For example, for systems which build the map in real time, like simultaneous localization and mapping, or SLAM, or visual odometry, and so on. So in these cases, it's very important to remember that you first need to come up with some sort of common reference frame, typically by aligning the ground truth and the candidate trajectory in order to meaningfully compute these metrics, because this metric doesn't really mean anything if the reference frames are completely off. Anyway, back to our task. So now that we have a time series of these absolute trajectory errors, what can we actually do with it? Well, one starting point was kind of the baseline way of interpreting and working with this metric, which is computing the mean, the average. So you can express all of these errors in the vehicle frame and then compute your mean error across, like you can compute the mean error along the road, you can compute the mean lateral error, you can compute the mean yaw error, whatever. But the mean errors on their own don't tell you the full story about the robustness of the system. So another approach is to actually look at where each error exceeds a certain threshold, for example. And this way, you can actually catch all the instances where localization is bad enough to potentially affect a downstream task. So, for example, to potentially affect motion planning in a self-driving car or the user experience in an augmented reality app. And in terms of what this threshold should be, we'll actually talk a little bit about this. It's very much an open problem. I have some slides about this later on. But for now, we can look at a quick case study where we plot some sign localization error over time. So in this graph, we can identify two of these weird peaks. And these actually indicate places where your localizer has some sort of error spike. And these are very likely areas where we should be focusing our investigation and our improvements. And fixing these errors might actually not really lower our mean error that much, but it will definitely improve the overall performance of the system. Okay, so just to recap, we saw that absolute trajectory error, or AT, is a very versatile building block for more interesting metrics. But at the same time, we also made a few assumptions about our setting. So some of these assumptions are that we assumed those, that there's n poses that are candidate poses and there are n ground truth poses. So we assume that we have the same number of poses and they are synchronized. But if this is not true, it might be necessary to, for example, interpolate the ground truth or formulate some other representation for your trajectories rather than sets of points. So if you remember back when we were talking about asynchronous modeling for simultaneous localization and mapping, again, if your ground truth and candidate poses are at different frequencies, then you have to solve the asynchronous problem anyway, even if you don't actually have asynchronous sensors. We also focused on localization metrics where we don't expect compounding drift. So for simultaneous localization and mapping or visual odometry, like I said, this does not hold. So then you need to look at other metrics like relative pose errors and that family of stuff to actually quantify the performance of those algorithms. Okay, so localization ground truth is the next step, right? Because all the metrics we saw right now, they require some sort of reference ground truth trajectory. But the question is, where do these trajectories come from? Because a ground truth, high quality, centimeter accurate, or whatever trajectory is not really something that a human can annotate. And typically we compute these trajectories offline in batch, possibly jointly with the map reconstruction itself. So there's multiple families of how to kind of come up with these ground truth trajectories ahead of time. But broadly speaking, there are a few major sort of areas. So the most obvious way is to use some sort of controlled environment, either motion capture systems or even just a simulator. And then you have extremely accurate, if not perfect, poses for a robot and then the associated observations. However, this can be very expensive and not very scalable for the motion capture system, or it can have limited realism in the case of simulation. Another option is to post-process your GPS and IMU trajectories in batch, not necessarily using any of the other sensors. So just optimizing these trajectories jointly. And this can easily be set up out of the box for many inertial navigation systems that you can kind of get off the shelf. But of course, this will still not be very accurate everywhere, and it will definitely not work when GPS is unavailable. And the kind of ultimate solution in this case is jointly estimating the trajectories and the map using large-scale simultaneous localization and mapping, or SLAM. And this has the potential of producing the best performance, but can be difficult to implement and scale from a practical standpoint. But once you put in the actual energy to do so, the benefits are huge. And it's also worth noting that the strategy itself that you use to compute this kind of information is critical for the task at hand. So philosophically, not even just in localization, but more broadly in machine learning, the idea of ground truth can sometimes be quite elusive. And the way we actually estimate your ground truth, or the way you define the label taxonomy and classification or whatever, might actually bias you towards certain solutions, even though in the grand scheme of things, one might not actually be better than the other. So this paper by Brahman et al. Talks about this from the perspective of localization. And it's a very interesting topic to learn more about if you want to localize at scale and evaluate these things, because it shows that the rankings of the state of the art can actually change depending on how you actually compute the ground truth. So we looked at how to measure how good the localization system is. We looked at the ground truth, but there's still one gap in our knowledge, which is how good do we actually need to be, or how low do these metrics need to get before localization is solved. And an interesting thing to point out is that a lot of the metrics we saw so far, like absolute trajectory error and its derivatives, are based primarily in terms of minimizing some sort of ego trajectory estimation error. But in self-driving, we primarily care about safe, comfortable rides to the user, which are actually motion planning metrics. So the question is, how can we actually evaluate the localization quality in terms of these end tasks? So as we saw in the perception and prediction talks earlier today, pretty much all autonomy systems that leverage maps in some capacity, they must at some point in the architecture actually fuse the sensor representation with the prior map information. So one classic example is you might have voxelized LiDAR that is embedded with some LiDAR backbone, and then you rasterize your map or do whatever, and then you have your map backbone. And then maybe you concatenate or add element-wise your resulting feature maps, and then you have your headers that do things like detection and motion forecasting, and maybe you're computing some cost volume for a planner or whatever. And the thing here is that if your localization is off, then these embedding branches will work fine on their own, but the aggregation itself will be off. But the question is, okay, so if it's a little bit off, if it's very far off, how will this actually impact system performance? So specifically, the question we want to ask is, how do localization errors, or you can extend this to just mapping errors more broadly, how do they actually map into autonomy errors? So how big does a localization error need to get before something like motion planning actually has an issue? So we analyzed this a couple of years back in a paper that was, it's kind of early stage in this area. And it's by no means a definite analysis, but it can give us a sense of how sensitive these autonomy systems are to things like localization errors. And these kinds of analysis can also serve as a foundation for more detailed analysis later on. So the idea here is that you took a very large test set and a joint perception and prediction model that was trained, in this case, with perfect map alignment. And the idea here is that you can then perturb the pose of the vehicle in the snippets and analyze various system metrics as a function of how much you actually perturb the pose. So the first thing that you can look at is, for example, detection metrics. Here we look at mean average precision. And as you increase the translation error on the x-axis, you can see how this mean average precision goes down, because higher is better. So we observed that in these plots that as we increase translation error, as expected, the metric gets worse, but not by a lot. And it's actually more sensitive to rotational errors. And there's a similar trend in motion forecasting where, again, in this case, it's an error. So lower is better here. And again, the error starts increasing, but it doesn't increase as quickly as you might expect, or at least as we expected. And then similar things happen for motion planning, where your collision rate of your, the hypothetically planned open loop trajectory versus, the other actors in the scene doesn't increase as much with translation errors, but it does so with rotational errors. Because rotational errors fundamentally map to larger displacement the farther you go, basically. By the way, rotation here means yaw. So we perturb kind of the heading of the vehicle. So yeah, this also happens when you measure the error between the open loop planned trajectory and the ground truth human trajectory. So this can kind of give us a sense of what it means for localization to be good enough. Because if we are still within the range where we see that downstream tasks don't really get affected, then that gives us a good sense of what a threshold should actually be. Okay, so now we established how we actually measure localization goodness. We can also, we can actually start thinking about how to actually solve the task of localization. And we can look at online localization. And a common element in localization methods is that you need to integrate new observations in order to reason about the state of the vehicle. And observations can take a very wide range, from things like direct sensor readings, like direct coordinates that you get from your GPS software, all the way to some predictions made by a neural network interpreting the scenes. So we can look at several high-level families of localizers grouped by the type of observation that they use. So some of these categories use, for instance, geometric alignment. They might use some sort of semantic matching. They might use some sort of LiDAR reflectance matching, or camera to LiDAR matching for scalable localization. So the first category we'll look at is semantic matching, which essentially leverages these compact semantic layers that we saw in HD maps, like lane lines and signs and so on, which can be stored very compactly. And the idea here is that at runtime, the car can recognize some of these elements, like you do some sort of online mapping, and then you match them against the information that you have in the prior map in order to localize. And while this can work with very compact representations, because these cues are fundamentally very sparse, these kinds of approaches are not really always able to achieve centimeter level accuracy, and might drift even further if there's no semantic cues at all in an area. On the other hand, geometric alignment methods rely on aligning LiDAR point clouds to pre-built 3D HD maps. And these methods can be very accurate, and they typically rely on well-established and conceptually simple methods that can be very robust to outliers, like the iterative closest point algorithm, or ICP. And the downside of these methods is that they can still have difficulties in geometrically degenerate environments, like tunnels and bridges, because there you basically keep seeing the same geometric pattern over and over, so you cannot fit your observation uniquely. And furthermore, they also typically require good initialization for convergence, although with global registration methods becoming more and more mature, this is no longer a very hard limit. And finally, storing and building these 3D geometric maps can be very challenging and expensive in and of itself. We can also cast localization as an incremental neural rendering task, and then fit a new camera reading to a pre-trained neural radiance field of our scene. And this kind of localization in practice can be done by essentially freezing your actual reconstruction weights and just running the optimization process a little bit by only updating the pose of your current camera image. And the benefits of this is that you can now share representations, for example, between simulation and localization. You can still get photometrically accurate results, and you can just do this sort of localization purely using cameras, for example. But of course, there's still some downsides, which is that these kinds of optimizations are still typically computationally demanding, and sometimes they might be less robust than some more traditional image matching. LiDAR reflectance matching is yet another family of methods for building a map with LiDAR intensity imagery and then matching online observations using some sort of 2D cross-correlation or template matching. And they can be more robust than pure geometric 3D methods, especially in mostly featureless environments, as long as there's some intensity patterns. And they can also be implemented in a very efficient manner while producing highly accurate results. But just like the geometric methods, they still have some limitations, like requiring pretty good initialization. And the map storage costs are also pretty high because they amount to essentially storing a lot of pretty high resolution images, which can add up pretty quickly. And the methods also typically require very precise LiDAR intensity calibration, which can limit their scalability due to the difficult nature of kind of per beam intensity calibration of LiDAR. Although this can be overcome with some recent work that kind of learns these agnostic representations. So now that we saw kind of a fraction of the world of online localization, we can also look at a few high-level methods for how to potentially approach global localization. And global localization essentially involves estimating the vehicle pose without any prior knowledge of where you are. So for example, they can be used even when online localization methods might fail and the vehicle needs to kind of reinitialize its state. The challenges with global localization are a lot of the similar challenges that you also saw with online localization. So, the same place can look very different depending on the time of day or whatever, the season. So you need to factor these things into your method. So let's look at several categories for how to actually approach global localization. One of the most common approaches is using something like GPS or its higher fidelity custom RTK. And as we saw in the hardware section, real-time kinematic approaches, by leveraging differential GNSS and carrier phase measurements to estimate the pose of the car, they can get really, really high accuracy readings without any prior knowledge of the environment, provided that you have available base stations for these corrections. Of course, the downsides, like I said, is that you still need the satellites to be visible in order to do anything. And if you want to have the centimeter level accuracy of an RTK system, you typically rely on these base stations to be available. And your receiver is also typically needs to be higher end. Another category of methods for global localization is these so-called pose regression methods that essentially learn neural network mappings that take some sort of sensory encoding as input and directly predict a pose for the robot, with the classic method in this area being PoseNet. And these methods are very fast, but there's some evidence showing that they still don't have the ability to scale to very large environments yet. And on the other hand, retrieval-based methods can be slightly slower, but that they do have the potential to scale to much larger environments, even though they might require a lot of memory to do so. Hybrid methods Essentially, we rely also on local features. So essentially, instead of describing the whole scene as a single vector and then using this to do some sort of retrieval like we do in the retrieval-based methods, here you extract local descriptors, which can be off-the-shelf SIFT style things or learned descriptors, and then you do some sort of local matching to localize. And more recently, it's also common to learn the pooling of deep local features into global descriptors in order to obtain a coarse pose that is then essentially refined with the local matches. So you learn some local features, you learn how to pool them, you get a global descriptor, you retrieve your candidates with this global descriptor very efficiently. And then once you have these candidates, then you rely on the more expensive local feature matching to actually refine everything. And a downside of these local features is that storage requirements now become higher than just pure global matching because you actually need to store descriptors and the actual images in the database. But there's a lot of work going into actually compressing the descriptors in the map or pruning the maps and so on. So things are getting a bit better. So to recap, in this session, we learned about what localization is, how we measure it, and how to compute the ground truth. And we also looked at how to analyze the impact of localization performance on the system as a whole. We also went through several approaches for both online and global localization, albeit only from the perspective of observation modeling. So there's entire textbooks on how to do the actual inference and state estimation, but there's just no time for that. So there are many areas of active research in localization, like improving the robustness, using multiple sensors, for example, using radar or LiDAR, localizing with one modality into another. So maybe use LiDAR to build a map and then a single monocular camera to match against your map. You could do cross view matching to localize in satellite imagery with a phone camera. There's a lot of work like we saw to reduce the reliance on HD maps altogether with online mapping and all that stuff. There's a lot of cool stuff that's happening in online calibration to reduce the reliance on kind of old school calibration that's done with calibration patterns and so on. So like I said, there's some references both on this slide as well as within the, they're within these individual decks as well as right at the end. So if you want to learn more and dive deep, some of these textbooks on robotics are really cool, especially if you want to learn more about geometry and 3D. Professor Tim Bauerfoot's textbook, if you get the second edition, really cool, highly recommended. And with that, I think I'm done.